Hello. Okay. Hello, everybody. Good night. Thanks for being here today. I'm going to talk about the discovery of the rarest of the decays, which is, of course, Be2 muons. But first, let's see what a BS meson is. A meson is basically a particle formed by two quarks. And in the case of the BS meson, these two quarks are the bottom and the strange quarks, as Jaco explained before. And one of the main properties of this BS meson is that it's a really short-lived particle. Actually, it lives only 0.00015 seconds before decaying into other particles. And one of these decays is actually the decay of the BS meson into 2 muons. That is the one that I'm going to talk about today, which is actually really awesome. Here you have the two diagrams in the standard model that make this process possible. In this first side, you can see the B and the S quarks, which form the BS meson. Then there is something weird happening here, and then we have the 2 muons. And the same thing happens in the other diagram. So what happens inside here is called quantum loop. Thanks to these quantum loops, this kind of decays are allowed in the standard model. But actually, I just wanted to say that physicists can be creative too, and we can be funny sometimes. Actually, if you turn around this diagram, and then these two legs here, you put them down, you would never see it, but this is the penguin diagram, right? And then for the other diagram, we have the box diagram. And actually, those are the official names for this kind of diagrams. So we talk about this a lot in the office. But BS2 is not only awesome because of the name of the diagrams, but also because it happens very, very, very rarely. So actually, if in case of these two diagrams, there would be a new particle here, for example, a dark matter particle, then the effects would be, that would have an effect on the properties of this decay. And just to give you an idea, from the standard model, we know that only 3 every billion strange B mesons decay into 2 muons. So actually, this number here can change to 2, to 4, 5. We don't know yet if we include dark matter candidates in the loops, in the quantum loops that I've showed you before. But in order to study this, we need to measure the BS meson, right? So we need to produce it. And for that, we have an amazing, powerful machine, which is the LHC, where we accelerate protons at high energies, and then we collide them. And in this collision, a lot of particles are generated, as you can see here, a bunch of particles, lots of them. And these collisions happen inside the detectors. We are going to focus on one of them, but just let me say here that one of these particles can be a BS meson, the one that we are interested in, right? So then, in order to study what is happening with these collisions and the particles that are generated in them, we use the LHCb, which is one of the detectors in the LHC, where B stands for beauty, because as you can see, this is beautiful, right? So for this LHCb detector mainly focuses on the study of the B decays, as I've said, so all the particles that contain a B quark. And for our own BS2 decay, we are going to focus on the vertex locator, which tells us actually where the BS has decayed into the 2 muons, so exactly the decayed point. Then, of course, muon stations, because we are working with muons, so if they are called muon stations, that might be because of something, right? And there we can detect the muons. And then we also have the magnet. And the magnet, it's really helpful because we can infer the velocity of the particles using the Lorentz force that you might recall from high school. So let's travel with the BS, but I've told you that it doesn't live long, right? So actually, it decays only after 17 millimeters after the PP collision point. Actually, this is good. Sometimes it decays even earlier. So that's the only thing that we can say about the BS. Now we have to focus in the muons, and let's see what happens with the muons. So the BS decays inside the velo, the vertex locator, and then the muons can travel to the muon stations. As I've told you, these trajectories are bended because of the magnet. They are charged particles, so depending on the charge, they will bend in different ways, and also in the velocity. And that's actually really useful because we can infer the velocity of the particles and then the momenta, which is something that we work a lot with. But let's see a nice and real event, right? So this is one of them. This is actually the LHC. I think you cannot see it properly because of the light. But as you can see, we have the two muons here. Those are the trajectories of the particles. We call it tracks. And actually, we don't really see the muons, so we don't really see them flying. The only thing we see are those small dots there, which are energy deposits. So basically, when the muon travels through the detector, it interacts with the detector, and then it leaves energy deposits, and that's where we actually detect. And in order to reconstruct these tracks, because we don't really know how it has traveled, right? Then we have really complicated algorithms, and people work a lot to do this. And we can actually know, oh, this muon came from here, and actually it came with the other muon that we detected. But things are more complicated than this. Actually, this is an event in the LHCb. So if you can tell me which two muons we have to look at, then please tell me now, because that will save probably 3 years of my PhD. So in order to do this, we have something that is trigger. So basically, the trigger selects the events that might be interested for further study. And in our case, these events are the candidates that can be a BS decaying into two muons, right? So in our case, the trigger focuses basically on the muons that come from the same point. But this is not the only thing that we need to take care of. Here is actually part of the results from the last analysis, and these points here, the black points, they are data. So this is actually data taken in the LHCb, and these lines here, they are the error bars. If there was a decay here, so if we could see a BS to mu mu decay here, we would see a bump in the data. And I don't think we can see something, right? Well, there is a small bump here, but that doesn't count. So, no, we cannot see anything. And actually, this needs a lot of study. So after years and years and years, and getting old and everything, we finally managed to find the BS to mu mu decay. Actually, you can see here the nice peak, right? And this is amazing, because actually it was the rarest decay discovered ever in the LHC so far. So we have to be too proud of this, because I'm not sure if you remember that I told you that from the standard model, only 3 BS mesons decay into two muons out of 1 billion. So that's actually really complicated to see. Although we are really proud of this, the error bars, as you can see here, are really big. So there is room for improvement. And we are working on that, actually. And we are mostly interested on the height of the peak. So this can tell us the number of events or the number of BS that decayed into the two muons. And actually, this is really important for the next slide, because this is the current state, and if we find new physics. As I've told you, we found it in 2015. And so far it's in agreement with what the standard model says, so basically the theoretical predictions, but the errors are still too large. This is the experimental value, and this is the standard model value, the theoretical one. And actually, just let me emphasize that this 3.00 is the height of the peak, and these values here are basically the errors given by the data. And as you can see, the experimental and the standard model values, they are different. They are quite different. But the problem is that the uncertainty in the experimental value, this one here, is also quite big. So far it's in agreement, but it might not be if we have more statistics, right? And then, if there was new physics, so for example, a dark matter candidate in the loop, something like this, where you have the dark matter candidates there. This is a new physics diagram, so this is something that is not present in the standard model. Then these values will change from the standard model. So these two values here will be completely different. And this is just by counting the number of events, the number of BS mesons decaying into 2 muons. But it's complicated, as you have seen. So BS 2 muon is indeed awesome, right? It's one of the most sensitive searches for dark matter particles, and we are getting there. But the errors are still too large, and because we only have a handful of events. But we are keeping measuring new data. We are working on that, and probably you will find some results in 6 months, more or less, or even a bit more. So stay tuned, because we are getting there. Thank you.